Let's meet our home galaxy, the Milky Way. A galaxy is generally a massive gravitationally bound system, a collection of stuff, basically, consisting of stars and stellar remnants, an interstellar medium of gas and dust to produce more stars, and an important but poorly understood component tentatively called dark matter. If we were able to remove ourselves from the Milky Way and get a bird's eye view from above, we would see our galaxy looking something very much like this, with spiral arms sprawling out like spinning tentacles around the massive bar in the center. In it, you'd find nearly 240 billion stars, with an additional 10 billion stars worth of ISM material, and even a supermassive black hole of nearly 4 million solar masses at the heart of the galaxy called Sagittarius A star. Over the years, we have managed to observe far out into the distances of the galaxy and determine its structure and motion. We have a pretty good understanding of it now, considering we know where we are with respect to other parts of the galaxy. Really, we can only observe out from our location since, well, we can't really be anywhere else but here on Earth, around the Sun, in this quiet little corner of the entire galaxy. If we flew around now and were looking edge on at our galaxy, we would see that it's not perfectly flat. In fact, there's some thickness to it. The thickest part of our galaxy is the bulge at the center, which is highly concentrated with stars and stretches nearly 20,000 light-years wide. It contains the central bar that we saw in the previous image and is home to a lot of stars, gas, and dust. The disk in the galaxy itself is the widest portion, stretching 100,000 light-years wide from one end to the other and a few thousand light-years thick. It's in this disk of the galaxy that we see the spiral arms extending outwards from the central bulge. Surrounding the disks and the central bulge is a faint spherical halo that extends past the visible components of the galaxy and is home to several stragglers of our galaxy's components. Now, the presence of stars in the galaxy should be no surprise to us by now. We should be quite familiar with stars. They come in singles, binaries, triples, and in systems of stars containing many more than a handful, anywhere between hundreds to thousands to millions of stars. These are called clusters, and these are the groups of stars that formed at the same time from the same giant molecular cloud and from the same trigger that initiated the star formation process in the first place. We first saw these in our discussion of stellar evolution, so now let's focus on them a little bit more and see what they have to offer. There are two types of star clusters: open star clusters and globular star clusters. Open clusters are generally groups of stars that are loosely bound to one another and move together through space. They may or may not be gravitationally disrupted as a result of their interactions with the nearby ISM from which they formed. We really only ever see hundreds or thousands of stars in these open clusters, and they are most often found in the spiral arms of the galactic plane with a trademark blue glow. Globular clusters, on the other hand, are spherical collections of old stars that often remain gravitationally bound to one another after they formed. These globular clusters tend to contain many more stars than what you would find in open clusters, ranging anywhere from hundreds of thousands to millions of stars, often densely packed at the center and less so around the outer fringes of the cluster. Since the stars in these globular clusters tend to be older, these clusters are often seen as yellowish-orange due to the tendency of these older evolved stars to be a little bit more red than the brand new ones. These globular clusters orbit the galaxy's core at extremely large distances in the galactic halo. Looking again at a bird's eye view of a spiral galaxy like the Milky Way, we can see that the globular clusters can be found in the halo and the open clusters in the disk. Even observations of other galaxies like the Andromeda have shown us that star clusters can be found in other galaxies too. This view of the constellation Sagittarius is actually littered with open and globular clusters at various distances and locations. We'll focus on two in particular: globular cluster M55 and open cluster M23. Their differences are obvious. One is a loosely bound grouping of stars, while the other is a more heavily concentrated spherical collection of gravitationally bound stars. How old are these clusters? Now, one way to tell is to plot the stars in each cluster on an HR diagram and analyze the main sequence turnoff point, like we did for globular cluster M55 previously. But is there another way? The answer, in short, is yes. One additional method of determining stellar ages is to analyze the star's metallicity. The metallicity is the percentage of a star's or a star cluster's matter that is not hydrogen or helium, and it can give you an estimate of that particular star or star cluster's age. Elements including lithium, silicon, carbon, tin, calcium, beryllium, literally any element other than hydrogen or helium, are referred to as metals by astronomers. So the metallicity of stars is determined by the abundance of these elements in the star's chemical composition. In fact, we can look for and find solar siblings, stars that are formed from the same gas cloud and in the same star cluster as our own sun. The star HD 162826 is one such solar sibling found as recently as the year 2014. It was actually the first such sibling to be found, based on the fact that not only was it determined to be similar in age, but it had the same chemical composition as our sun. That would make sense if the two of them likely originated in the same giant molecular cloud. Now, another way to classify the ages of stars is to define 3 generations of stars. Much like you can find a fair mixture of kids, teens, adults, and elderly in a crowd of people, you can also find similar generations in populations of stars. Population 1 stars are young, metal-rich stars or stars that have a high metallicity. Population 2 stars are slightly older stars, with less metal than what can be found in population 1 stars, so we refer to the population 2 stars as stars with low metallicity. A third category, called population 3, refers to the hypothetical generation of the first stars ever to form. And since the existence of these heavier metals was only made possible through thermonuclear fusion, these population 3 stars contain no metals, since nothing existed during their time other than hydrogen and helium, so these are the metal-free stars. But the thing is, they were so massive that they burned fast, burned bright, and died young. So they don't exist anymore. There's none left. So now in terms of the stellar populations, what would you say? Will open clusters be composed of population 1 or population 2 stars? What about globular clusters? Remember, population 1 stars are stars that are metal-rich and young, and population 2 stars are metal-poor and old. If you guess that open clusters contain population 1 stars and globular clusters contain population 2 stars, great, you've done well. If not, go ahead and rewind and review this video one more time to get the idea. Now, all of the various things that we have discussed so far about our Milky Way galaxy begs the question, how do we know all this? How did we find it all out? The answer is through observations. We know so much about our galaxy by observing the light that comes from those very distant stars. But how are we able to see the stars on the other side of the center of the galaxy? There's too much dust in the way for us to actually be able to see through to the other side. So, how can we? We have to use other wavelengths. If optical doesn't let us see through the Milky Way, then we have many other options we can use instead. You can actually calculate the wavelengths associated with these frequencies or energies and check your answers if you pause the video here. Challenge yourself, do some math for fun. I know it may be a tall order and completely unfavorable, but it's good practice. It keeps your mind sharp. Now, particularly, the 21 centimeter line comes in very handy in trying to understand our Milky Way galaxy. If you recall from a little bit ago, the 21 centimeter line corresponds to the spontaneous spin flip of a neutral hydrogen atom. It is not the same mechanism through which hydrogen emits visible light because, well, 21 centimeters is a radio wavelength and is often how we see atomic nebulae, H1 regions. The discovery of the 21 centimeter line in 1951 not only helped astronomers map the galaxy, but it also gave us a tool to observe the galaxy's motion. We can analyze the Doppler shift of the 21 centimeter line to determine whether the hydrogen under observation is moving towards us or away from us. Recall that when the source and observer move away from each other, the wavelength gets stretched, making it longer, and in this case, that wavelength becomes redshifted. Similarly, if the source and the observer are moving towards each other, the wavelength contracts, making it shorter. So in these cases, we have blue-shifted light instead. So by looking at the 21 centimeter line in galactic spectra and observing its shifts, we can tell if stuff is moving away from us or coming towards us. Now, from our little quiet corner in the galaxy, If we pointed a telescope out to the night sky and observed the Doppler shift of the 21 centimeter line of hydrogen along our line of sight, we would be able to see how the neutral hydrogen moves within the galaxy. Remember, there's quite a bit of it too, almost 10 billion stars worth of neutral hydrogen. These observations gave rise to our understanding of the galaxy's rotation by observing how the stuff in it revolved about the galactic center. Now we can see the same concept in these side-by-side images of the spiral galaxy M83, where neutral hydrogen clouds are concentrated in the spiral arms of the galaxy. We are able to detect their presence by observing the 21 centimeter line emitted from them, and any shift in the wavelength determines the direction of rotation of the galaxy. Astronomers have observed and measured the motions of the stars throughout the galaxy to see how the galaxy as a whole can rotate. The stars in the disk of the galaxy orbit the galactic center in the same general direction together, but they bobble up and down in their orbits, giving the disk its thickness. The stars in the bulge and in the halo orbit the galactic center not only in different directions, but at random angles and inclinations with generally higher velocities than the stars in the disk. By measuring how the stars orbit around the center of the galaxy, astronomers have determined that our galaxy has what we call differential rotation. Now, differential rotation is the type of motion associated with a rotating object, but different parts of the rotating body rotate at different rates. For example, imagine a CD or a vinyl record spinning. Different points on the surface of the disk will rotate at the same speed, regardless of their distance from the center, since they are physically bound to the rotating surface and must be moving along with it as well. So the velocity at point A is the same as the velocity at point B or C or D. This, however, is not differential rotation. This is wheel-like rotation. This, on the other hand, is differential rotation. When objects that are orbiting a common center do so at different speeds at different distances, much like the planets in our own solar system do, we call this type of motion differential rotation. Now, this is the concept that provided the basis for our expectations of how our galaxy's rotation would be, until we actually observed it. Our expectations led us to believe that the galaxy's differential rotation would look something like this, with faster rotation at distances that are closer to the center and slower rotation at larger distances. But this is what we saw instead. The fast rotation at the center is still there as expected, but now it's maintained throughout the edge of the galaxy, even at the larger distances. So the galaxy's rotation is definitely not what we expected. If there was no material beyond the visible edge of the galaxy, then the orbital speeds at the outer edges of the galaxy should decline, as shown here in the expected rotation curve. But what was observed instead showed that not only is the rotational velocity of the galaxy still up there at those extremely large distances, it actually seems to be speeding up the further out you go. So what's going on here? What's with this gap? Maybe the Milky Way's rotation is anomalous and other spiral galaxies actually rotate like we expected. So astronomers checked that out, but as it turns out, that's not true either. Even other galaxies like the Triangulum galaxy, whose rotational curve is shown here, has the same distinct gap between its expected velocity curve and what was observed instead. Even more so, these spiral galaxies show the same type of rotation. So what could possibly be the root cause of this? Well, there is a theory to answer that question, and it's called dark matter.